Hello, my name is Jamie Newhall. I'm an engineering management major and I'm the team lead.
Hello, my name is Felipe Pera, and I am a systems engineering major, and I am the procurement lead for this project.
Hi, my name is Sebastian Govia, and I'm a systems engineering major.
Hi, my name is Adam Hoffmeister, and I'm a software engineering major.
Hello, my name is Ian Johnson. I'm an electrical and computer engineering major.
Hello, my name is Gloria Melanie Romero, and I'm an electrical and computer engineering major.
Tucson Electric Power has tasked us with making a smart energy grid system for their consumers, all of us. The smart energy grid is really an evolution of a traditional energy grid that identifies issues within its system and uses smart aspects such as autonomous rerouting, load balancing, and demand response to increase reliability, efficiency, and sustainability, as well as bring down costs. Our team has developed an efficient and reliable energy grid designed to generate, store, and distribute power utilizing traditional energy sources as well as renewable ones. Our design primarily uses Simulink, a software environment within MATLAB, to create our simulation. Our simulation file itself incorporates electrical grid aspects such as energy production, transmission, and distribution in defined blocks. Along with our Simulink file, our system uses a combination of MATLAB for scripting and post-data processing, a JavaScript-based server, Python, and a graphical user interface in order to produce the necessary functionality and flexibility for users. These users will be able to manipulate certain parameters and specifications within the simulation via the GUI, resulting in unique outputs for each respective set of parameters, which can then be looked in further to improve system efficiency and ensure that the energy grid is operating accurately to real-life examples.
As for our approach to the problem, we derived our system requirements by analyzing current energy grids and building upon their foundational components and abilities. Our key requirements highlight the basic processes within an energy grid, such as generation, load balancing, and distribution. Additionally, we needed to consider that energy grids might change and look differently in the future. So, we incorporated smart aspects into our requirements, which include the ability to autonomously identify issues affecting the grid and reroute power accordingly to minimize outages. Lastly, we determined that our project must allow users to interact with the simulation, and this will be done via our graphical user interface.
However, the primary issue we encountered is that Simulink is not configured to incorporate comprehensive software overhead during runtime, meaning you can't effectively call a MATLAB script mid-simulation. To account for this, we separated our simulation into particular clock cycles to create a pseudo real-time experience. A primary application script will initialize input variables for Simulink. Then, the simulation will run for one clock cycle and extract all resulting data for processing. This cycle will continue until the simulation is signaled to end by the user.
Another aspect we needed to take into consideration is the user experience. In an industry setting, there will primarily be two types of testers. First, engineers who want to continuously integrate changes into the smart energy grid model, and second, individuals with a test team, likely without as strong of a technical background, who simply want to run tests and analyze simulation data. For the latter, Simulink is a fairly complicated environment that is not easy to interact with. To address this, we created a graphical user interface that contains a simplified yet interactable environment. Furthermore, we created a web server that would manage communication between the GUI and the Simulink application that is hosted on a separate device. This would prevent the user from ever having to install dependencies such as MATLAB or Simulink. This also addresses an issue we found where running the Simulink and GUI on the same device to be a fairly resource-intensive process.
Here is what our final simulation looks like. Starting from left to right, we have our power generation, the transmission substation, the distribution substation, our Phoenix utility, and our neighborhood modules. Within our power generation module, we have 4 subsystems, one for each of our sources. Our simulation uses natural gas, coal, solar, and wind. We use controlled current sources to manage the power generation of our simulation. Moving on, within our transmission substation, we have a transformer to step up voltage and a resistor in case of a power surge. The distribution substation has the same structure, but it steps voltage down to an adequate level for distribution to the simulated homes. The Phoenix utility has a circuit breaker that can be used to send excess power to our neighboring utility of Phoenix. Finally, our neighborhood module contains 3 subsystems, one for our 2 urban neighborhoods, one for our 2 suburban neighborhoods, and one for our 2 rural neighborhoods. Within these neighborhood blocks, we have varying power lines, which accurately represent the type of customers using approximate distances in kilometers. There are also circuit breakers that can cut off power to a sector and/or redirect power between sectors. Lastly, there are multiple sensors that provide data for post-simulation processing.
So going into a quick snapshot of our Unity GUI, we have the clock cycle updating with each received data package from the server. And we also see, for example, the power generation is updating in accordance with data sent from the server. For our subsystem tests, our approach was to create scenarios that test the system and cover multiple requirements. We have a nominal test, 2 rerouting tests to test different edge cases, and a load balancing test. For our analysis approach, at the end of the simulation, a script generates an Excel file with all data for analysis. For our nominal results, we see our power generation is within range in terms of distribution and in terms of meeting its minimum generation requirements. For our rerouting test, we have several different results, but just to take a look at a single example, when several lines go down in this particular neighborhood sector, power is rerouted, so on the next clock cycle, those lines continue receiving power. And then for our load balancing results, we see when demand begins to exceed energy production will trend upwards and be able to match that demand. And for our distribution results, we see Phoenix Utilities is receiving energy and it receives it in accordance with our energy production. For our system integration results, we mainly want to test the GUI functionality works and updates in accordance with MATLAB code, and we analyze the results package after each run to ensure that the functionality is in accordance with expected behavior.
The first lesson that we learned with our project is that we wish we had started development a lot sooner with both Simulink and our graphical user interface. With Simulink, we were worried about choosing the wrong package and spent a lot of time researching different packages, but we have since realized that if we had started working with Simulink sooner, we would have saved a lot of time with our MVP1 and our MVP2. With the graphical user interface, we were worried about working on it too early and causing too many changes within the project to make that work futile, but we have also since realized that if we had started sooner with the graphical user interface, we would have saved a lot of time in that aspect of the project. The second lesson that we learned with our project is that we wish we had started working with a Simulink specialist a lot sooner. We met with a specialist in spring semester, but if we had met with this person in the fall semester, we would have saved a lot of time in the development of our model itself. Overall, our project has encountered many obstacles, but we have been able to overcome them. One of the great aspects of our project is how cheap it is. We've been able to save about $2,000 in our overall budget. Another great aspect of our project is we've been able to meet all of our sponsor requirements. To ensure we are meeting these requirements and getting the proper output data, we have completed full subsystem testing. This includes testing both the Simulink and the code separately and together to ensure that our simulation and the AI decision making is working as intended. The only testing we have not yet completed is full system integration testing. This includes combining the Simulink and MATLAB code with the GUI itself and ensuring that all of that communication layer is functioning as intended. We are confident, though, that we can complete this testing by design day. Thank you for your time.